minus 2, 1 and 1. So it says that find a row reduced echelon matrix R which is row equivalent to A. Okay. So what was the definition of row reduced echelon matrix? Yeah. Okay. So for a row reduced echelon matrix, the exact definition is something like for okay. I'm just scratching the definition in terms of the
all the zero rows are grouped together at the bottom of the matrix. If there is a non-zero entry in any row, that should start with a 1.
Yes.
That is for the leading one.
So there's
as you go down, the leading ones move to the right. That's it.
yeah. So the exact definition is row reduced echelon matrix is A. R is row reduced. Then B, all rows of R having all its entries zero occur at bottom of matrix. Then C, if rows 1, 2, dot dot R are the non-zero rows of R, and if the leading one of row I occur in column Ki, and I is equals to 1, 2, I, then K1, K2, K3, K. This is the definition of the row reduced echelon matrix, right? So previously we also know what a row reduced matrix is. So for a row reduced matrix, you can. This is an example of row reduced matrix. You can show that 0, 0, 1, 2, 0, 0. Then 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 2. This is an example of row reduced matrix, right? Okay. Sorry, we are just discussing the old stuff.
Oh, okay. Then
So-
I didn't miss anything.
Yeah. So this is an example of row reduced matrix. So for a row reduced matrix, what we need to consider is that for every non-zero row, the entry that is the first entry that is non-zero is 1. That is the leading one, right? And in that column, every other elements is 0. Okay.
That's a great.
Yeah, that's a definition of row-reduced matrix. Then, for row-reduced echelon matrix, you just need to consider these two, that all rows of R having all its entries 0 occur at the bottom of the matrix. Okay. So, okay, let me just here's this one.
To get 0 row is
Yeah.
at the top, not at the bottom.
Let me see. 0, 0, 0, 0, 0.
No, what I was suggesting here.
Jim. Okay. Still, it is a row reduced matrix, right?
Still.
It is a row reduced matrix. Yeah, this is a row reduced matrix. But when we are considering the row reduced echelon matrix,
But this is
the
not the echelon.
no, this is not the echelon
Oh,
matrix.
that's
For row reduced echelon matrix, the second B, the definition, it says that all rows of R having all its entries 0 occur at the bottom of the matrix. So then if I just erase it and I write it like this is a row reduced. Still, this is not a row reduced echelon matrix, but here the 0 row is at the bottom of the matrix, right? Now, for the third condition, it says that if rows 1, 2, dot dot r are the non-zero rows of R, and if the leading one of row I occurs in the column Ki, where I is equals to 1, 2, dot dot r, then K1, K2 is less than K2, is less than K3, is less than Kr. Okay. So now,
right.
yeah. So this is the first column, right? So this is the second column, this is the third column, this is the fourth, this is the fifth, and this is the sixth. Now, to make it a row reduced echelon matrix, what I need to do is,
But before that,
yeah,
why don't you say what is K1, K2, K3
Yeah.
is in this?
okay. So for K1, this is just what it says, that if rows 1, 2, dot dot r are the non-zero rows of R, and if the leading one of the row I occurs in the column Ki, then K1 is less than K2. Okay, so now,
So K is the column index.
yeah, that is a column index. So for this one, this is,
K1 is the cell.
yeah,
So this is K1.
yeah, this is,
That's not K.
That is not
K,
K1.
sorry,
K1
That should be K2.
this is K2, this is,
Write down K2 later. Why K2 comes before K1? So please write K1 first. K1 is equal to what?
this is K1,
K1 is equal to. Please write K1 is equal to what? 3.
yeah, this
Yeah.
is 3. Okay, then for K2 is equals to 1, and yeah, I put a 0 there, right? So, and K3
K3. 6. Oh,
Not that one.
no.
Okay,
Then
so-
but
K3 is equals to 6, right?
Now tell us if K1 is less than or less than K2 is less than K3, does that hold here? That does not hold.
That doesn't help. So it is not a row reduced echelon matrix, right? So what I can do is, if I write this matrix as 1, 0, 0, 0, 1, 0, then 0, 0, 1, 2, 0, 0, yeah, then 0, 0, 0, 0, 0, 1, 0, 0, 0. Now you can compare this matrix with the
How did we come to this matrix from the previous? Can you identify what was the elementary row operation?
so yeah.
By means of which operation we came to the latter matrix from the former matrix?
Row swapping.
Yeah.
Which and which row?
That
So this 101, the second row went up. First and second row.
yeah.
Second.
So this is the third type of row.
Right.
Yeah. So there are three types of yeah. This one is the row redistribution matrix. Row redistribution matrix, and we use the third ERO to bring it down, right? And now you can compare that this is actually fulfill all the requirement of the definition. And what was the definition? That R is row reduced. The first one is it has to be a row reduced matrix, right? So is this matrix a row reduced matrix? Row reduced, yeah. Then the second one, it tells us that every 0 rows in R has to be in the bottom of the matrix, and there is this one row that is a 0 row, right? And it is in the bottom of this matrix, right? Okay. And the third condition, now consider this. This is K1 is equals to what? K1 is equals to 1 here. Then K2 is equals to K2 3. Then so K3 equals to 6. Now you can compare that 1 is less than 3 is less than 6, right? It is a row reduced matrix. So do you have any other question? Okay.
For the exercise, how do we approach?
Okay, so
We do
for the
EROs, right?
you have to do what?
On the elementary row operation.
No person in this matrix. So what will be the first ERO you are going to apply in this matrix A? You have to consider the first row first, and the first, yeah, it is start with 1. That means this is the leading one, right? This is the leading one. So to make the row reduced echelon matrix, what you need to do is, yeah, so every other elements in this column, these elements has to be 0. Then what you can do is you can apply R1 plus R2 equals to R2 prime, right? And for row 3, you can apply minus 1 times R1 plus R2 equals to, sorry, R3 equals to R3 prime. Right? So then this will be, so, okay. Okay? Then 1 2 1 0,
Okay, got it.
1 2 1 0,
So you can skip it.
yeah,
So these are just laborious approach.
yeah. Okay, then the second question that it was asked is what? There are part of the question.
So these are all the same.
Okay, so it says that to A and then invertible 3 cross 3 matrix P such that R equals to P. So it says that you have to show that after the performing all these ER rows, you get a matrix R which is row equivalent to the matrix A, right? So, and the question asks that you have to show that R equals to P A, where P is what?
P is the
Is a
invertible symmetry.
3 cross 3 invertible matrix. How you can show that? Yeah, there was a theorem I proved in the last class.
Yeah, that is like invertible. So identity matrix.
Yeah, so you have to first define what a elementary matrix is, right? So, and definition of the elementary matrix is what? So, elementary matrix
You just need to remember which ERs we performed and then construct those elementary matrices.
So the elementary matrices is defined by elementary matrix matrices that can be obtained by performing a single ERO on the identity matrix.
It's only 1 year, right?
Yeah.
Did you show that the algorithm of finding an inverse?
Yes, in the last class. So then can you tell me what was the elementary matrices of this matrix? What are the elementary matrices of this matrix? This is a 2 cross 2 identity matrix. Yeah, so the first one is I can swap then 0, 1 and 1, 0. This is one, then another.
Multiply, addition.
Okay, so the first one is I can multiply it by number C by an entry element that comes from the field. So C0, 0, 1, that is also a elementary matrix. Then you can construct another matrix from this. Which one is that? Yeah, then,
Two different rows.
okay,
So
so
1 plus C.
1,
1 plus C.
no,
Oh, sorry, 1 plus and 1 C.
Yeah.
0.
0, 1. This is also a elementary matrices of this type, right? And I also show in one of my previous classes that so for every ERO there is this so for every ERO this condition that E of some matrix A is equals to some elementary matrix E times the matrix A. This holds, right? So why this holds? We can just simply give an example to this problem, and let us just consider A is a 2 cross 2 matrix, and this is just simply, let's say, 1, 3 and 4, 6. So if I perform a ERO in this matrix, a single ERO, and let's consider this just multiplying it, the first type of ERO with a number C, I mean the entry coming from the field, then this will be what? C, 3C, 4, 6, right? Now, so this is the elementary matrix we got by performing the first row on the identity matrix, this, right? You understand it, right? Now, let's just, so there was just simply C 0, 0, 1, and if I multiply this with 1, 3, 4, 6, then this is just simply what? C 3C and 4, 6, right? And this is equivalent to this one, right? Okay, so okay, now if I perform a sequence of a finite sequence of ERO on a matrix A, then so let's consider this in this way. So I'm performing EK E1 of A, then what will be that? This is equal to no,
This is equal to another matrix.
yeah, so I will get something like EK dot dot E1, right? And all this matrix multiplication is possible between this. So I can define just simply this as P, and this is just K, right? So what is P here? P is the product of all the elementary matrices.
And so that is invertible matrix.
Yeah, because elementary matrices are the invertible matrix, and I proved it. So do you want me to go through the proof again? Okay. So P is equals to,
another result needs to be,
yeah,
you have the elementary matrices and these are invertible. What else do you need to show that P is invertible?
okay. So Syed is asking why this is P is invertible.
If I understand correctly, so if we multiply P with the invertible, actually the definition of a particular matrix and its invertible produces identity.
Yeah, but what is the another property you need to consider to show that P is actually an invertible matrix, and we prove that.
Sufficient to just state the fact that all the elementary matrices are invertible to prove that P is invertible.
No.
Don't you need the fact that the product of invertible
Matrices
is also
invertible. So we used and
to prove that P is invertible.
Yeah, okay, so all these elementary matrices are invertible.
Right.
right
And
then
we also need the fact that the product of invertible matrices.
Produces one invertible.
yeah. So a simple example and again can be AB.
These are all square matrices, right?
Yeah, otherwise you can call for the inverse.
So just consider, let's A is the invertible matrix and the inverse of A is just I'm considering A inverse and B, this is B inverse, right? So now that means A inverse is just the identity matrix. I'm just ignoring the left multiplication here, and also B. Okay, so I need this actually. A inverse A is equals to identity, and B inverse is equals to B inverse B is equals to identity, and then the product of these two matrices, invertible matrices A and B, the inverse is simply B inverse A inverse. Okay, so how can you show that this is actually This is true. How can you show that this is true? You can simply, yeah, you can just multiply this. So if I check the left multiplication, this is something like A. So P inverse A inverse times A B is equals to. So I can multiply these two, and which property of the matrix multiplication I used here? Yeah, associative. Then this is just simply B inverse identity B. Then this is B inverse B, and then this is identity. So the left multiplication is true. Then you can similarly show that the right multiplication is also true, because then the B and B inverse will be multiplied first. Right? Okay. That means this matrix P is actually the product of all these invertible elementary matrices, and this is also an invertible matrix. And since we can construct row reduced echelon matrix from this matrix A by performing a finite sequence of ERO on this matrix A, then what you can show is by using this analogy here. I just gave you this. You can just write the matrix A with the product of the elementary matrices, right? And that will be the row equivalent matrix too. So that means that P is actually what? The invertible 3x3 matrices. Okay. So is there any other thing that you want to discuss? Okay. So do you have any other question? Okay. Then should we start the new topic today, or you want to discuss something else? If you have any other question, I can discuss it today, because no one is coming, I think. So
I think the same logic will go for 5.
no, I don't have the code actually. Okay, so yeah. This is it. The question number which 5, yeah, is invertible and find A inverse if it exists. So this is not actually a similar problem. So we discussed in the last class that what was the algorithm you can follow to construct the inverse matrix of a given matrix, right? And there was something like I proved a theorem as well that you can perform the, so just consider this. If you consider a matrix A, and if this matrix is actually invertible, then you can do is just construct this matrix. Okay. Then the ERO that will reduce this matrix A will also bring this matrix I to the inverse of that matrix. Okay. So a simple example can be like 1, then 2, then 0, and 1. Yeah. So if I just set it like 1 0 0 1 and use the algorithm of the inverse matrix, this is just simply what you can just to make this a row reduced echelon matrix. What you are going to do?
R3 2 times R3 minus 2 times R3 plus R1.
Yeah. So you are going to do minus R2 2 R2 plus R1 equals to R1 prime, and then this will be 1 0 0 1 and 1 minus 2 0 1. So, and we can check that this is actually the inverse matrix of this matrix. Okay. So that is the problem that given in the exercise 5. Any other problem? Okay. No problem.
So we from vector spaces. Page 23, please. Some exercises.
We didn't do exercise.
I don't give any exercise from the vector space. I just
Maybe we can discuss.
yeah, I just introduced the definition of the vector spaces in the last class. So the definition of the vector space was in the explicitly I discussed in the last class, right? Now, just simply to remember, I use this one thing that I gave you.
I have a recommendation.
Okay, so
Work out an example with matrices with complex elements. I think there are examples or exercises
in the exercise in the book.
where you have matrices with complex elements.
Yeah.
So that you have the field of complex numbers.
Okay.
And you have to use elementary row operations using complex numbers.
Yeah.
I think you should try to solve one of those problems
As well. So
where you can go beyond the
field of real numbers.
real. I think there are some problems, right?
Yeah.
In Hoffman too.
Yeah.
So try to solve one of the problems here.
I guess only one.
Yeah.
Number 2, I guess. Go to page 26.
Do that.
The same, like it says 1.
Which
Yeah.
page 26?
So this one.
Oh, book page.
Good reason.
Yeah. It,
Do
The same.
so
2, 0,
there
I,
are 2
1 minus 3 minus I.
2 0 I
1 minus 3 minus I.
1 minus 3 minus I
2. Sorry, I 1 1.
I 1.
what did they ask?
So
Same like the this same
We
with
do
this
one
one.
exercise. We already did session 11.
okay, so he asked to find out the row radius matrix of this matrix. Yeah. So can you work this example out? So for the first row, what you are going to do for the first row?
We divide by this.
The first row, year row, then this will be like 1 0 I over 2, right? Then 1 minus 3 minus I 1 1. This one. Then what will be the operation? So I use the operation half times R1 equals to R1. Right? Okay. Then what you are going to do next? So to do that, what will be the operation? Actually, you are going to minus multiply row 1 with minus 1. Then you are going to add. Yeah. No, actually they are not same because we defined only the addition, right?
Oh, okay.
So then this is like minus 1 times R1 plus R2 equals to R2 prime and minus I times R1 plus R3 equals to R3 prime. Then this is just simply 1 0, I over 2, 0, minus 3. Okay, so minus I over 2 minus 2 minus I over 2. So this is minus 3I over 2. Okay, and then this is 0, this is 1, and this is 1.
Minus half. It should be.
Yeah, this is half. No, this is actually 3 by 2. Yeah, this is 3 by 2. Right? Then what will be your next operation? So you, what is what?
R2 divided by minus 3.
Yeah. So you can do it like 1, 0, I over 2, or you can do another thing here. Can you tell me which ERO you need to do to make it? Yeah. So you can do just simply 0, 1, 3 over 2, 0, minus 3, minus 3I over 2. I used third ERO here, right? Then what will be your next operation? You are going to multiply row 2 by 3 and add 3 plus 3 with R2 plus R3 equals to R3 prime. And this is simply 1, 0, I over 2, 0, 1, 3 over 2, 0, 0, multiplying this 9 over 2 minus 3 I over 2. Nine minus 3 over 2. This is it, right? So what will be your next operation? You are just going to make this a 1, right? So you can divide it by this, and again you can perform the other two to make this and this to 0, right?
So for reduced
Yeah.
matrix, you have to make the third row 0.
No, you are going to multiply with the inverse of this element, right? So this will be what, 1, 0, I over 2, 0, 1, 3 over 2, then 0, 0, 9. Sorry, this is just 1. And the operation was 9 minus 3I over 2 inverse with R3 equals to R3 prime, right? Then what you are going to do, you just multiply R3 minus 3 over 2 R3 plus R2 equals to R2 prime, then minus I over 2 R3 plus R1 equals to R1 prime. Then this will be 1, 0, 0, 0, 1, 0, 0, 0, 1.
I have a question. Is this 3 times the complex matrix that you started with? Is this the invertible?
This matrix.
Yeah. It is working. because same we understand. If it is row equivalent to an identity, because it is row equivalent to identity matrix, that is why it is inverted. We had a theorem that
And it's a consequence of that.
Right? Very good. So, do you understand what Sir is saying? So, what he was saying is that since this matrix,
I mean, why it is inverted? That's the question.
yeah. So, since this matrix is row equivalent to the matrix I, this one, identity 3 cross 3 matrix, and there are I think in the last class or in the previous in the last class, yeah. So in the last class I proved that this any matrix that is row equivalent to the identity matrix, that matrix is what? Invertible matrix. And we use that theorem to construct the algorithm to find out the A inverse, right? And I started this example, this one. Okay. Okay.
Can a non-square matrix be row equivalent to identity matrix?
No.
So when a matrix is row equivalent to an identity matrix, it is necessarily a square matrix.
Okay, so yeah.
So when there's complex inverse,
Yeah.
it is like this.
Yeah. Can you tell me why this exists? Why this exists? Can you tell me? Why this inverse exists?
because it is the element of the field.
Yeah. Because it is the element of the field.
It's a multiplicative inverse of that element of the field. Multiplicative
Just straight take that.
So when we define the field, we say for every non-zero element in the field, there exists a inverse. Right?
So you don't need to come algebraically prove this. You don't need to.
That was the definition.
Just by definition.
Yeah.
I mean, you don't need to show the calculation.
Yeah.
Yeah, you can also do that.
Do that.
That guy is going to be 2 over 9 minus 3. So I think he wants to see
Okay.
that in the form of a plus I.
So 9
Please do that.
minus 3i over 2. That was the entry in the 3, 3 entry of that matrix, right? So now if I multiply it with 9 minus 3i over 2 inverse, this is simply 9 minus 3i over 2 times 2 over 9 minus 3i, or just simply, okay, let me show. 1 over 9 minus 3i over 2,
This inverse meaning this
9 minus 3i over
yeah,
2,
this is reciprocal.
9 minus 3.
This fractional reciprocal.
Yeah, but there is still one thing to be shown, that 2 over 9 minus 3i belongs to the field,
Yeah,
and that should be expressed in the form of a plus I.
okay, so I can just 9 minus 3i over 2, okay, so
9 plus 3i.
this is this.
9
Okay.
plus 3i.
Okay, let me just construct this in this way. So this is 1 over 9 minus 3i over 2, which is 2, 9 minus 3i, and I can multiply the numerator by 9 plus 3i times 2 over 9 minus 3i with 9 plus 3i, right? I can multiply this, and we know that the matrix multiplication, the complex number, the multiplication of the complex number is defined by a plus ib times c plus it is equals to ac minus bd plus I with BC plus AD. And we also know that if Z is a complex number, then there exists a conjugate of that number. And if Z equals to simply A plus IB, then Z, conjugate of Z is what? A minus IB, and we know that Z times Z bar is equals to A square plus B square, right? Now use that definition here. This is 2 times 9, so let me just multiply this. 18 plus 6i over 81 plus 9, which is equals to 18 plus 6i over 90. That means 18 over 90 plus 6 over 90 I. This is the inverse of this number, right? So, do I need to show them that if I multiply these two, this will go?
I made a blue.
Yeah.
I made a blue.
Okay.
You get it.
Yeah, I understand. Okay. So, okay. Then any other question? Do you solve all the problems? So you can do something like you can LaTeX all this, and yeah, if you have time, you can make a copy of that. And sir, if you do that, I will ask Tibu sir to open a Google Drive or something else where you can post that and we can create an archive on that.
I don't know how to do LaTeX, but I will learn.
Okay, yeah, this is
I will
very
learn.
pretty simple, and you can just
Maybe this could
if
be
you
a
start, you will
motivation for learning.
yeah, yeah. Eventually, you have to learn LaTeX.
Or do I write it in my book and then I take view side of scan and then close it?
Yeah, LaTeX will be better because we are going to make an archive of that.
Okay.
So, yeah. Typed
Okay, I will.
will be pretty much helpful. Okay, so if you don't have any other question, I can start the vector space today, the motivation of the vector space today. Okay, so again in our first class we discussed some two definition of the vector. The first one is the physics definition, that was what the vector so every vector has dimension, sorry, magnitude and direction. And the second definition was used by the CS people. They defined the vector as vector a vector is a list of numbers of numbers.
I have a
Yeah.
question. In physics, people also maintain the dimensionality of the elements, right?
Yeah.
Like say meters. But in CS, they don't care about the dimensions also.
Yeah.
What
So
units, I mean.
Yeah.
Units.
so list of numbers. Then now first today let us define the what we mean by list.
I guess the
Yeah.
main thing is not the exact numbers, it's like list of values.
And
It could be
sorry,
pure numbers,
I just defined it in terms of the list of entries
entries here.
that can be like numbers, elements,
Yes.
or any other thing. Okay. So now first let us define what we mean by list. So definition. Suppose n is a non-negative integer, a list of length n is an ordered collection of n elements. So there is this which might be numbers, other lists, or more abstract entities. Separated by commas and surrounded by parentheses. So, a list looks like x1, x. Okay. So as you can see that even the list can be consist of other lists as well. Okay. And there's this one thing you need to consider, that collection of n elements in list collection of n elements which might be numbers. Yeah. Ordered. Yeah. This is very important. An ordered collection of n elements. So can you tell me what is the difference between x1 x2 dot dot xn, or just simply just consider 1 comma 1 and 1 comma 1. This is a set and this is a list, right? So this is just simply what, this is just the set 1, and also 1 comma 2 2 comma 1. Can you tell me what is the difference between these two?
I can swap them, but I cannot swap in the basic list.
Yeah, so in here you cannot swap like 2 1, you cannot write it like this, but in here you can like definitely yeah. So when you are considering list, you have to consider the order. Okay, so now there is this another thing that physics people consider derivative, and vector is translationally invariant. Okay,
Translation doesn't.
translation doesn't, yeah, if you have the same direction and same magnitude of that vector, then translation doesn't actually matter. So to do that, let us just consider two points, and the first point is let me consider this 2 1 and another point 1 comma 2. So this is an element of what, 2 comma 1 is an element of R2, right? And this is also an element of R2. So what is the equation passing from these two, passing by these 2 points? Can you construct the equation? Yeah, the equation is
X minus 2.
y equals to minus x plus 3. Okay, so I'll just use the formula like y minus y1, that is 1 divided by 1 minus 2 is equals to x minus 2 over 2 minus 1. Then if you simplify, this will reduce to this, right? Now okay, so let us define addition in R2. So a generic element of R2 is just simply a comma b, and if I take another element a prime comma b prime, these two elements belongs to R2, and I can define a addition between these two by what, a comma b plus a prime comma b prime, this is equals to what, I can simply add these two,
A plus A prime.
a plus a prime comma b plus b prime, right? And I also can yeah, so I also can define the scalar multiplication or multiplication by the field entries by c times a comma b is equals to ca comma cb, where c belongs to the field, right? So you can show that under these two operation, it is actually a vector space. R2 is a vector space. Okay. So you can check all these operations like can
C can be, F can be any field, or you want F to be the set of elements?
So for here, I want it to be the real numbers for this example. Okay, so you can check all these operations like commutativity, associativity, neutral elements, inverse elements, associativity of scalar multiplication, distributivity of yeah. So this one is like c times u vector u plus vector v is equals to c u vector plus c v vector, and this one is c plus some another number like c plus k u vector is equals to c u vector plus k u vector. Okay, and the last one is the unit of the multiplication, that is 1 times unit vector is equals to u vector. Okay, so you can check all these 8 properties satisfied by these two operation if I define it like this. So under this operation, R2 is what? R2 is a vector space. Now, and I already showed you that if I consider the point 2, 1 and 1, 2, these 2 points belongs to the vector space of R2, right? Now, so yeah, if I just okay, so the line segment, so the equation of the line is y equals to minus x plus 3, right? Now, okay, what is this one?
Gmail.
No, no, no. I think I forget this one's is this one. Rahul. Yeah, in front of me. Oh, yeah,
Do you want it on split screen?
yeah, split. Thank you. So, just okay. So, what I'm considering is this is the equation of this line, right? Okay. So, um, how do I do this? Rahul. ডেসমসের ইয়েগুলো কিভাবে আমি চেঞ্জ করতে পারি
কোনগুলো?
জাস্ট 0 to 5 না কনসিডার করে
the divisions.
yeah divisions
মানে কি মানে you want shorter divisions. Settings is step এখানে you can like specify 0.5, so upon 2.5 settings and step x axis y axis.
once you so
Manually zoom in after changing the abar reset first.
okay
Zoom in করার পর then you change the step.
okay thank you. So as you can see from here that this is the point 2, 1, right? And another point is 1, 2 is simply here, right?
I think you can put
Yeah, okay, I will do that. So, oh, sorry, not this one. Yeah. So now I'm restricting these 2 points, 2 comma 1 and 1 comma 2. Okay. So and this dot is moving from 2 comma 1 to 1 comma 2. Now, so as we know that from the definition of the vector space from the physics, that the vectors 1 comma 2 and 2 comma 1 is simply, I can like 1 comma 2 minus 2 comma 1. So just use the triangle law. This is this, right? And if I just, sorry, this is the R2 plane, and this is 1 comma 2, and this is 2 comma 1. Okay, so what I can do is I can this is the definition of something radial vector in the physics, right? So now just O A B. Then what will be BA? We know that if we add OB plus BA, this will be equal to OA, right? And simply BA is equals to what? OA minus OB. And you can change the direction, like AB, this will be what? OB minus OA, right? Now just consider this in this way, that if I, yeah, OB minus OA. Okay, so BA is what? If I just consider the coordinates, then this is 1 comma 2 minus 2 comma 1, right? Then this is what? This is 1 minus 2 comma 2 minus 1, and this is what? Minus 1 comma 1, right? So this vector BA is simply is something like the dot that moving from the point 2 comma 1 to 1 comma 2 in that direction, right? Now you can define the vector O, and let's just consider the point minus 1 comma 1 as the point C. Okay, now what is OC? The vector that starts from the center to that minus 1 comma 1 point. And if you see, this is in that color, the purple, this is the vector, right? So these definitions, and we know that in physics we consider that vector is translation invariant, right? So the dot that moving from 2 to 1 to 1 comma 2, if you translate this to OC here in the purple one, the direction and the magnitude will be same, right? So in physics we consider something like a vector has a magnitude and a direction, but when we consider the R2 as a abstract vector space, we simply just define the addition and scalar multiplication, and we can add two points of the R2 plane, right? And everything, the definition that physics people used and the CS people also used, like that. So 2, 1 or 1, 2. These two, this is a list, right? This is also a list. And if you just use this notation of OB, BA, OA, these are the what? These are the definition comes from the physics, right? Now, all these things you can generalize by just considering R2 as a abstract vector space. Sorry, R2 is an abstract vector space where the operation defined by so okay, I don't need this operation defined by A plus B, sorry, A comma B plus A prime comma B prime is equals to A plus A prime B plus B prime, and the scalar multiplication C A comma B is equals to C A comma C B, right? So abstractly you can think R2 as a yeah. So under these two operations, R2 is a vector space. So is it possible that R to the n, is it a vector space? If I define the addition and scalar multiplication in the same way I define for R2, is it a vector space? Is it a vector space if I define the
Yes.
addition and scalar multiplication? Then this is a vector space, right? Okay. Now, so why we are generalizing this definition? Why we are consider the so much generalized definition for vector space, and we are doing it in mathematics? Why this is needed?
So we can handle many variables.
Actually, not main variables, with different type of objects. Like so. Now, if I just simply, if I consider the collection of 4 cross 4, sorry, let's start with the simple 2 cross 2 matrix under the operation one matrix addition and scalar multiplication of matrix. Is it a vector space? Oh, sorry. So and over the field. First, let us consider just the reactance. Is it a vector space?
It should be vector space.
Can you tell me what is the so for the vector space, what we need to show that there exists a neutral element in the vector space, right? Can you tell me which one is the neutral element in 2x2 matrix? Zero matrix, right? So the neutral elements is 0, 0, 0, 0, right? So for a generic matrix like A, B, C, D, we know that for every vector B in the vector space P, there exists minus V belongs to V such that minus V plus V is 0. Can you tell me what is the inverse, additive inverse of this matrix? Right? The additive inverse will be minus A minus B minus C minus D. Right? Okay. And why the associativity holds? No, matrix addition is associative. Right? We're not considering the multiplication here. Matrix addition is associative. That's right. Okay, so we can generalize this definition of M cross N matrix. Okay, so
These are minus V vector, right?
yes, sorry, sir. Minus B. Minus B. Yeah, 0 also goes.
So there are two zeros, as you can see.
Yeah.
One zero is in the field, and the zero vector is in the vector space. To distinguish zeros.
Okay. So
Yeah. Now tell me one thing. Zero times V vector. Can you please write it?
sir, I'm just
Did you
yeah.
prove it?
No,
Oh,
I'm
you-
going to prove this. Okay, so there are a couple of things that I want to prove here. Is let's just start with. So before proving this, so I want to show them the vector space of the functions. So if S is a set and R is the field,
Sometimes we say that it's a usual way of writing that V is the vector space over the field F.
Yeah.
If your scalars are coming from that field.
Yeah.
And you say that V is a vector space over that field.
that is what I used here over the field of. Okay, so if S is a set and R is the field, even what Sir was suggesting that I can consider the generic, so it's field F. So just consider this. F is the field. What I can do is the space of functions from the non-empty T set S to the field F given by S comma F so the addition in this vector space is defined by F plus G, where F and G are the vector and S is an element, is F of S plus G of S. I don't think I need a bar here, right? So, and the scalar multiplication C F of S equals to C times F of S. Is it going to be a vector space under these two operations?
Okay, so here is the
It is a vector space.
Why? Yeah.
I want to say that when you have CF on the left, so it's a comment.
Yeah.
CF, C is an element from the field, so and these two dots are not the same.
Yeah.
Although we wrote the dot,
But these two are different. Like, just consider this to be a
the bigger dot, smaller dot.
smaller.
One is composition, right?
One is the scalar multiplication in that vector space of functions. And on the right side, that dot is the multiplication in the field F.
Right?
These are two distinguished dots.
So, what Sir is saying is this dot is the multiplication in the space and this dot is the multiplication in okay. So just consider a simple example like if we consider something like if you consider R to be just simply a real field, sorry, F to be a real field, then this will be what? These two operations simply. So if I consider F is R, yeah, then this operation, like if I multiply C numbers, C with F evaluated at this element, this is what? This is just C times F of S, and we know that F of S belongs to R. So this multiplication is just what? The multiplication in the real, yeah. But in this multiplication, it is not in the real field, right? Yeah, it is in the vector space. Okay. Okay, so
That means, say that I'm representing f of s with an arrow that in the first case I'm just extending the length,
yeah, exactly.
and in the second case,
This is just simply you are mapping from one vector space to another vector space. So
Or-
the idea is, can you show that this is actually a vector space? So to show that, you have to show that this if this set satisfies all the 8 axioms of the vector space, right?
Yeah, but I had a concern.
Yeah.
If both of you understood, can you please prove out
Yeah.
these two? What does it mean by F plus G and C dot F? These two. us how this function is defined. So f plus g is a function where on the set,
Yeah.
and it is supposed to spit out an element in the field, right? That is why he has this curly f in the bracket. He has s comma bold-faced f. It means that it is a set of all functions from the set S to the field F. So now, in the first rule, it is telling me that f plus g is a function, and it takes as input S, and it is supposed to spit out a field element, and that field element that it spits out, f plus g, is that field element on the right, which is f of s plus g of s. F of s is the field element, which comes from what? Since f is a function, therefore f of s is in the field. So is g of s. So the field element that we are looking at is the addition of these two field elements. So as a matter of fact, the plus on the right is not the same as the plus on the left.
Yeah.
Either.
These two.
That plus is in the vector space, and that plus is in the field. Is in the field over which the vector space is defined. Now come to the second formula. In the second formula, it tells you that when you scalar multiply C with the vector f, by vector of course I mean a function, right? In this setup, a vector is a function. So C that dot f is going to be a new function. And that is how this new function is defined. C dot f is taking s as an input and spitting out an element in the field. And that field is what we have on the right hand side. C dot f of s. By definition, f of s is in the field because f is a function in that set. Curly f s comma bold-faced f. And C is the field element, and that dot on the right hand side is taking place in the field. It is the multiplication in the field. So there are nuances here that you need to understand. Very important nuances. And that dot is right in the vector space, the bigger dot. Okay? And everything is well defined.
Yeah.
On the right side, I have the field element because that dot is taking place in the field. And on the left hand side, everything is fine. Right? On the left hand side, in both these equations, the left hand side is a field element. The right hand side is also a field element. Do you see that the left hand side of both these equations are field elements? Left hand side, right hand side. Right hand side is also field. If the right hand side is field and the left hand side is not field, it don't make any sense, right? The
So-
left hand side, f plus g is not in the field, but f plus g acting on s is in the field.
After operation.
After operation. And c dot f acting on s also
In the field.
is
Okay.
there.
Well, thanks, sir, for making this clear. And so, can you show that this collection?
Why don't we just only say field? We don't say scalar field. It is a
Well, that is the multivariable context. We define what a scalar field is, but that is a different field. This is the algebraic field. This is the algebraic notion of field, but that is a different notion of field that he has defined in that course, right? He defined what a vector field is, what a scalar field is. It takes as an input a vector and spits out, probably in his case was a number or a scalar. That was a scalar field, right? So that he defined. But when in the context of algebra, by field we mean
Field that, so
there were some axioms.
there are 9 axioms a set has to satisfy
A
to
set
become
with two operations. One was addition, the other one was multiplication. So that we have considered that.
So this is this field, the algebraic field, and that field is something else. That is the in the context of multivariable calculus or differential geometry or other things. Okay. So so this is actually a vector space. Why? You can show that there exists a minus f, and in the f is comma f, so that minus f plus f acting on s is equals to what? This is simply minus f of s plus f of s. That means this is equal to 0. Why is this 0? Because this is what? And this is the additive inverse of this. Right? So in the vector space, this minus f is the additive inverse of f, right? Okay. So then the what is the zero vector here? Can you tell? What is the zero vector here?
I think it's just only in the above the C, the multiplication with the C, we define it to the 0, then to 0. The C
The zero?
composition with the bigger multiplication.
No, there is two distinct zero here.
Like
The first zero is belongs to
the field,
no.
the vector space.
Sorry. The s comma f and another zero that belongs to f.
You could put the
Vector symbol.
something like that. That will make life easier. Just a little bit. So now Jim is asking you if zero vector is a function, because in this setup, all the vectors are functions, right? How that function is defined? The zero vector is supposed to be a function. So there should be a rule. What is the rule? So zero vector and S is what?
This is equals to 0.
That's everything, or the field in the field. So this is how you define the zero function. It maps all the elements to the zero element. I can see that it's a function, right?
So what Sar is asking, can you see from this definition that this is a function?
Yeah.
Now, what is the definition of the function? So you have to consistent with the definition, right? So for every
S in S,
in the domain, there is a unique
function.
element. Yeah. So now if I consider 0 of s, that is 0, and 0 of s prime, that is still 0. So the 0 is unique here, right? And there is no restriction of choosing s and s prime, because s and s prime in the domain, right? So the definition is,
all the elements in the domain has to go to 0.
yeah.
Because I had a confusion, like say if I define a function, say at some point it will intersect the x-axis, then I can have a 0, right?
Yeah. No, that is not the case here.
Yeah, I get it. Yeah. I had a question.
Okay.
My question was that.
Okay, so okay, so let me give you some. So the definition, there is a definition. A vector V belongs to the vector space V is said to be a linear combination of the vectors u1, u2, un belongs to V, provided there exist scalars C1, C2, Cn belongs to F such that V vector is equals to C1 U1.
How long are we doing this?
So I think 5 more minutes. C2 U2 Cn Un, which is I equals to 1 to n Ci Un. Okay, so this is the definition of the linear combination here, and from this
But you did not discuss the matrix example. You didn't go back to that. You were supposed to. You told that after you finish the function example, you will go back to.
no sir, I already did. Yeah.
Oh, you already did?
Yeah, I already did. And I said that every m cross n matrix is a vector space.
The set of all
m cross n matrix is a vector space.
over the field.
Yeah, over the field. Yeah.
So
I didn't write it, but I say.
Did you understand that the set of all n times n?
M times n.
Oh, m times n.
Yeah.
Right. The set of all m times
n. So for this, I consider just the square matrix. So but I say that every m cross n, the set of all m cross n matrix is also a vector space over the field F.
So there is a nice notation for that. You can write it.
Yeah.
Bm sub m cross n bracket inside bracket we write F. Voltage F. This is the notation for this vector space. It means that if an element in this vector space is a matrix of size m times n, where the entries are taking values in the field F. That is a vector space. So he discussed 2 examples of vector space. Vector spaces. 2 nice examples.
Okay. So the last thing that I want to prove here today is C times 0 vector is equals to 0 vector for C belongs to field F. Okay. So how can we prove that?
You have to be able to prove it using the vector space
Axioms. So as you can see that we can do is like C times
There is no vector over.
C0 is C0 vector plus 0 vector, right? Why? Because 0 plus 0, 0 vector plus 0 vector is also a 0 vector. Everything add with like S plus 0, this is S vector.
Anything you add 0 is
0,
same.
same thing, right? So now what you can do is you can multiply this using the distributivity of addition, sorry, multiplication, and this will be c times 0 plus c times 0. This 3. Right? Now, what you can do is you can subtract, or you can just minus c times 0 vector plus c times 0 vector. You can add these two vectors in the both side, minus c 0 vector plus 0 vector plus c 0 vector, right? And then in the left hand side you got what? 0 vector. Why is that? Because for every vector in the vector space there exists a inverse vector. So then left hand side is 0 vector, and the right hand side, what I can do is I can use the associativity of addition, and this is 0 vector plus c0 vector, but the right hand side is simply, if you add a vector with a 0 vector, this is the c0 vector. That means c0 vector is equal
This is the
to,
power of axioms.
right? So every time sir taught me something, sir always said, like, you have to follow each and every step properly using following the axioms. So what you can do is you can 0 u vector is also 0 vector where the first 0 belongs to the field F. Okay, and these are the exercise for you to prove that -1 times u vector is equals to minus u vector. If you understand the axioms of vector space properly, you should be able to prove this too.
Similarly, you just use the axioms to get.
And I highly recommend to go through all the steps by, like, properly using the axioms in this way.
But is there a sequence for that? No.
No,
We don't need to follow a sequence dash.
no.
You see that the third result is a very non-trivial result. Although it may appear to be very trivial problem, but it's a non-trivial result. On the right hand side, I have the additive inverse of the given vector, right? We know that in vector space for each vector we have an additive inverse. That is the minus u vector. And on the left hand side, that is the scalar -1, or which comes from the field, multiplied with u vector. And that multiplication is taking place in the vector space. That's the scalar multiplication in the vector space on the left hand side. So these two, you need to prove that they are actually equal. It's a non-trivial result.
Yeah. And
But it is not.
yeah, and after you prove this, you can show that there is only one unique additive inverse in the vector space.
Yeah.
And I
That was not in the axiom.
no,
So
the axiom
because
is
the
there
exist-
exists a inverse.
okay. So the unit test part was not there. it was just the existence of the zero
Yeah.
in the axiom. So whenever in mathematics you have to prove some uniqueness, you assume that there exists two of them. Then you have to prove that they are equal. That proves that there exists a unique.
Yeah.
Is it clear how you
So okay, let me just give you a sketch of the proof. So let us consider V and W are the additive inverse of U. So what I can do is I can start from V and V vectors. Sorry, these are all vectors. Then V vector is equals to 0 plus V vector, right? Sorry, V vector plus 0 vector. Then since W is the additive inverse of U, V vector plus W plus U plus W, but I can use the previous one as well because addition is commutative, right? So, and then what I can do is I can use the associativity V plus U vector plus W vector.
So both are additive inverse. V and W both are additive.
Yeah, both are additive inverse. So,
we are assuming.
so then this is, but V is also the additive inverse of U, right? Then this is what? 0 vector plus W vector, and this is W vector. So I started with V and I end up with W vector. So it proves that the additive inverse of the element U is the unique one. But when I defined the vector space, there was this axiom that for every vector V, there exists a additive inverse of that vector. There is no uniqueness in the definition. Okay.
And then why aren't we just redefining the definitions and say that because
No, you don't need to.
That is not an axiom. Axiom is something that you are not able to prove.
Yeah.
So since you are able to prove the uniqueness, you don't attach it with the axioms.
Okay. It's more like assumption, basic foundation.
Yeah. The axioms are there. You cannot prove the axioms. You have to take them
Because they're given.
Yeah, and this is not attached with the axiom since you can prove it. This is a consequence of the axioms.
Okay.
Okay, thank you very much.